Okay, so as a little bit of a summary from last time and also a bit of a chat, we're going to talk about the different types of radioactive decay, alpha, beta, gamma, key properties of them. Obviously, we did do some of it in that table. I'm going to do a little bit, some additional sort of detail regarding them and just sort of what we can deal with in terms of those things. So, types of decay. So an alpha decay. Okay. So an alpha particle are helium nuclei. So 2 protons and 2 neutrons. Okay. Now, they generally, with alpha particles, they're generally always emitted with around about 6% of the speed of light. So they travel with a velocity of the order of about 6% of the speed of light. Which means they have a kinetic energy, giving them of around 6 mega electron volts. Okay, so they are the most energetic of the types of radioactivity that we have. Now, interestingly, with most alpha emitters tend to emit things with only sort of one discrete energy value. A few do a few different ones, but a lot of them will emit their alpha particles with a discrete value. Bismuth, however, does do about 6 different ones, ranging from 5.4 to 6.1 mega electron volts. But 97% of the emissions are at 2 discrete energies, 6.086 and 6.047 mega electron volts. So most isotopes that are alpha particles do so at a single discrete energy. Now, what this means is that therefore they kind of generally travel a certain distance through air before essentially just stopping. Okay, so this means they basically all get the same distance in air before you then, and it's why there's a very rapid drop off at pretty much about 2 to 3 centimeters, leading to a rapid drop off in their detection. After 2 to 3 centimeters in air. So you might remember sort of if you've got your unfortunately, so you might remember the demo from sort of GCSE where you have there's the little cup sources that look like that, and they're sort of held with tongs, and you've got your Geiger-Müller tube counting to a detector. And so what would happen is these things travel across, and this thing beeps whenever it detects something. So once you get around about 2 to 3 centimeters away, we get no detection. So if we were to graph kind of that, it's very fiddly to get. But what this means is we end up with a kind of number detected. Sort of range. What you tend to find is something that looks basically a bit like this. So they're all kind of detecting order, and then suddenly a very rapid drop off, and then something like that, where you get to 0, where that is the range through the absorber, or thickness of the absorber. So for something like if it's air, then this distance gets to be about 2 to 3 centimeters. If it's, say, sheets of paper, you might get 3 or so sheets of paper before it all just drops off, depending on what it is. You can throw alpha particles through things like very thin gold foil, because we can draw it out very, very thinly. But that is that's sort of what we kind of get. So irrespective of things, because they've all got the same energy, they generally are all going the same distance, and then sort of boom, it decreases very, very rapidly. So when an alpha particle is emitted, the atomic number of the nucleus decreases by 2, because we've lost 2 protons. The atomic mass decreases by 4. And just as a reminder, remember that these 2 numbers, or the mass number in particular, the true change in mass is different to that, because we've got to worry about the binding energy. But as far as like the actual numbers that we'd put, we'd end up with so if we have an example, we've got 2, 3, 8, 92 uranium. We'll go to 238. It's going to go down to 2, 3, 4, and that's going to go down to 90. That's an isotope of thorium plus 4, 2 alpha. So that is just a reminder of how to draw those things. So whenever we emit alpha particles, we are essentially losing mass. So we're losing energy from the nucleus in that way. So that is the method in which they are done. And that's kind of what we need to worry about with alpha particles. All right, let's go along here. Let's do beta decay, or beta particles. Okay, so I'll begin this one. So beta particles are either very fast electrons, which is a beta minus, or positrons, which is beta plus. They, they're emitted due to the change of quarks in the nucleon. So if you remember, a beta minus is where an up changes to a down. A beta plus will be where a down changes to an up. So that is the if you've got a up, up down will go to up down down, plus a beta minus plus an electron type antineutrino. So you'll also get a piece of antimatter coming out, because you've got a conserved lepton number. So alongside the beta particle, we also emit an anti-neutrino, which is what happens when you emit a beta minus particle, because that's matter, so you need some antimatter, or a neutrino, which is what happens when you emit the beta plus. So that's just a reminder of what's going on inside the nucleon itself. So this is an example of beta minus decay. So this essentially is a proton, so that is a 1,1p, and that goes to a 1. Nope, it's neutron to a proton. I managed to confuse myself. Up, up, down. I'm doing a positron emission, aren't I? No. The neutron goes to a proton. That's a neutron. Goes to up, up, down. Yes. Right. Okay. Whoops. My bad. Change that. Apologies. Sorry. So up, up. No, yeah, up, down, down. Doing it again. Up, down, down. Goes to up, up, down. So yes, that is a 1, 0 neutron has turned into 1, 1 proton. So that's a sort of a neutron decay plus that. So you can either think about it in terms of the quarks or the actual things, which is obviously my own silliness. So when we emit, now beta particles, are emitted with a range of energies. Up to around 1 mega electron volt. Now, the reason for that is that you don't know exactly where the beta particle has been emitted within inside the nucleus, and you don't know how exactly what direction it's traveling. So obviously, it's going to feel some attraction, or, from the nucleus itself. So so this is kind of where it goes. So beta particle emitted with a range of energies up to around mega electron volt. This leads to their absorption being approximately exponential. Okay, now this approximately, it's difficult with beta because as they collide with things, they can also knock electrons out of the things they hit. So you can end up with them detecting the other things and not actually the beta part itself. They can be an absolute, they can actually be, sort of thing. But what they would have is something that would look, a bit like thickness of the absorber. There's your number detected. Something a bit like that would be our kind of thing. Now that's that's our sort of beta particles. And that is the thing. Beta particles, though, they create a kind of like tortuous like route through something. So as beta particles try and travel through things. Because they're small, they kind of get hit and scattered around as they sort of try and travel. So they don't form a nice straight thing, where an alpha and gamma sort of travel nice and straight through material. So that is what happens here. Oh yeah, so with the beta decay, the atomic number will change by plus or minus 1. The mass number is unchanged. And there we go. That's our thing with that. Right, okay, let's deal with gamma. Okay, so gamma radiation is produced when excited nuclei release energy. As a wave. This often happens following an alpha or beta decay. So it's not something that is like, oh, okay, this is, this is something. It's something where this will occur afterwards. So the decay from an alpha or beta leaves the nucleus in an excited state, and then you get a gamma emission afterwards. So the energy of gamma ranges from about 0.01 mega electron volts to about 1 mega electron volts. So the most energetic can be on par with the energy that you're getting out from beta decay. So, however, as you've seen when we deal with X-rays, you can overlap things in X-rays, but it's defined as being, the gamma ray is defined as where it's come from. It's come from a nucleus, whereas an X-ray comes from smashing electrons into things. So yeah, so about 0.1 MeV is kind of a general sort of like thing. Now gamma rays are absorbed exponentially as they travel through a material, and this is called the Beer law. I think it's called the Beer-Lambert law. Okay, so this means that the intensity of the radiation that's terrible. Intensity of radiation decreases as, so let's do this. So we've got intensity I is equal to I0 e to the minus mu d. So we can say what this sort of means is that if we have a block of material, we've got our beam coming in, this is our initial beam, this is our beam coming out, and this is the thickness of our material. And so mu is called the absorption coefficient. And so now gamma radiation is, its absorption, we can sort of look at it as really this is not an equation that I think is given on the spec sheet, the thing you're meant to remember, but it could be something they give you and say, can you handle it? Because it's can you deal with it? It's like, because it's basically a thing. So this absorption coefficient depends on the material. So we can work out mu. So let's do a little sort of example. Okay. So 4 centimeters of lead reduces the intensity of gamma radiation to 10% of its original value. What is mu? Okay, and so we say, oh, okay, so we would have our new intensity is 10% of our original intensity. So we've got 0.1 I0, that's our 10% of our initial intensity, is equal to I0 e to the minus mu times 0.04. There's our centimeters into meters. Okay. So what we get is that 0.1 is equal to e to the minus 0.04 mu, and we can get rid of that by taking the natural logarithm. So we'd have the natural logarithm of 0.1 is equal to minus 0.04 mu, and that gives us a value of mu, and I need my calculator for this. So we have a value of mu of 0.1, so that's log of 0.1 over minus 0.04, and we get a absorption coefficient of 57.6, and the unit of it, because this is in meters, this must be in meters to minus 1, equals mu for lead. There we go. That's sort of a way in which we can handle sort of the absorption of these things as they go through. Okay. So it is a true exponential. Beta's very nearly, and often is, but if you've got thickness, then the intensity you detect will be an exponential decay. So that's what happens if we have a straight sort of a collimated beam going through something in a straight line. But equally, we've got to remember that gamma rays, gamma rays will also follow an inverse square law. So as gamma radiation is sent in all directions, the intensity also follows an inverse square law. Okay, so if you're dealing with just a gamma source that's kind of, just sort of there's your gamma source, well, it's giving off energy in all directions, making a across three-dimensional space, so a sphere. So that would mean that at a distance r away from the thing, the intensity is going to equal to the power of the source over 4 pi r squared. And what that means is that this sort of says if you double your distance, the intensity decreases by a factor of 4. And so that's how that works. Now, why that is important is why that is there is there's an example of Los Alamos where there was a chap called Libby Slotin who accidentally connected two parts of the core of what would become a nuclear bomb, and he flooded the room with radiation. And because he was closest, he received a fatal amount of radiation, whereas others around him actually survived because even though they were only a few meters away, they were, in terms of R, far enough away so the intensity over the period that they, the intensity was low enough so that during the time at which the two cores were connected, they did not receive a fatal dose of radiation. And that's kind of sort of what we have. Oh, look, it's gotten more to write each time as we went. So that sort of really sort of sums up the sort of the properties of the different types of radiation. We've got the fact that they're different, like, as we discussed previously, how they were identified, well, by deflecting in a magnetic field. This will go one way with its positive charge. This will go another way because it's negatively charged and has a smaller mass. Whereas a positron will have an equal and opposite sort of direction. Gamma rays undeflected by either electric or magnetic fields. And there is no real difference things. Sometimes you'll find that the way that they sometimes talk about there is a type of relativity trace that we use in medicine. Sometimes they've been identified by a little m. There's technetium, which is called 99m, and it's 99 metastable. It means it's basically it takes several hours before they generally emit the gamma radiation, and the M means metastable. It means it's good enough for you to hold on to for a long enough period of time before it sort of emits its gamma radiation. But yeah, that's those are the types of radiation. And yeah, I think that pretty much covers everything we need to talk about. So let's do a little bit of practice.